Hi, my name is Shahnawaz. In this lecture, we will study the convergence in Hausdorff spaces. Now, the condition that the finite sets in a topological space are closed is in fact weaker than the Hausdorff condition. Now, what do I mean? So, if we look at the say, let us consider R equipped with the cofinite topology, then one can easily verify that this is not a Hausdorff space. For if this is a Hausdorff space, then for any two distinct points, say x1 and x2, we can find open status, say u1 and u2 containing x1 and x2 respectively, such that u1 intersection u2 is empty. So this is x1 here, so we have u1 here, this is x2 here, this is u2. Now that means, so if this is the case, so if this topological space is Hausdorff, then for any two distinct points we can always find these open status u1 and u2 containing x1 and x2 respectively, such that their intersection is empty. But then this would imply now R being an infinite set and u1 and u2 being infinite sets because in infinite sets having the cofinite topology on them the open status has to be infinite because their complement has to be finite. Now if we look at this the complement, so this has to be a finite set because a set is open, so U is in the cofinite topology if U complement is finite, so its size is finite. Now u1 and u2 being being the open status, being the elements of this T cofinite, means complement of u1 is finite and complement of u2 is finite. Now u1 and u2 being elements of cofinite topology, so their intersection is also open, so this intersection has to be a finite set. But if we look at this intersection, this is same as the intersection of the complement of the their complement has to be finite. But if we look at this complement over here, this is going to be the whole R, which is finite set. So this topological space is not Hausdorff space. But if we look at the finite sets in this topological space, say let us take the set x1, x2, so on xn. So suppose this is of set V. So if we look at V complement, then this is an open set. Now why this is true? Because if we look at its complement, that is a finite set, and by definition of cofinite topology, a set is open if its complement is finite. So that means if we look at the complement of V complement, that is going to be V, which is a finite set. So that means V complement is open set. So V complement which is V, so that has to be a closed set. So the condition that the finite sets are closed in a topological space is slightly weaker than the condition of being Hausdorff space. Now for that very reason, we define the T1 spaces, or the topological spaces satisfying the T1 axiom. So we have this following definition. So a topological space say xt is said to satisfy T1 axiom if finite subsets of X are closed. So if finite subsets of X are closed. So one can note here, this topology is not Hausdorff, but it still satisfies T1 axiom, because in cofinite topology on R, the finite sets are closed because their complements are open. Now we have a following result here. So we have a theorem. So suppose, so let X be, so let X T be a topological space satisfying T1 axiom. Let A be any subset of X. So let A be a subset of X. Then a point X in X is said to be, so is a limit point of A if and only if A contains infinitely many, I mean, then this X is then this X is a limit point of A if and only if every open set containing X contains infinitely many points of A. So now the definition of a limit point changes in T1 spaces, I mean the spaces satisfying T1 axiom. So the definition, so for, I mean the definition of limit point of a set was like this. I mean, if xt is any arbitrary topological space and A is any subset of X, then we call X to be a limit point of A if every open set containing this X, say if every open set U containing X has a non-empty intersection with A. I mean, this U has to contain at least one point of A different from X. That is, if I look at this intersection, I mean, if I look the intersection of U with A except this point, so this intersection has to be non-empty, then we call this X a limit point of A. But if this space X is a T1 space, I mean if this space satisfies the T1 axiom, then what this theorem says, this theorem says this intersection has to be an infinite set, so its size has to be infinite. So let us prove this. So first we are going to assume that every open set U in X contains, I mean every open set U in X that contains X contains infinitely many points of A, then we are going to prove it's a limit point. So suppose every open set U in X containing X contains infinitely many points of A. So what do we mean by this? I mean, this is over U here and it contains X, so we say that this intersection, I mean the intersection of U with A, so we assume that this intersection is an infinite set, and we have to prove x is a limit point. I mean, we have to prove this intersection contains at least one point of a other than x. That is certainly true because this intersection is infinite set. So then u certainly contains a point of a different from x. Because this intersection, or so what is our hypothesis, what is our assumption? Our assumption is that this u is an open set which contain x, and this u contains infinitely many points of a. So if that is the case with every open set, then this u certainly contains a point of a different from x, and hence this x is a limit point of a. So hence x is a limit point of a. Now let us assume that this x is a limit point of a, and let us prove that this intersection is an infinite set. So conversely, suppose that this x is a limit point of a. Now what we have to prove? We have to prove this intersection is an infinite set for any open set u containing x. So let u be any open set containing x. So we chose this u, an arbitrary open set that contain x. Now what we have to prove? We have to prove this intersection is an actually an infinite set. So we want to prove so if this is the case, so what we have to prove? We have to prove this intersection is an infinite set. So suppose this is not true. Suppose u intersects with a in finitely many points. So suppose u intersects with a in finitely many points. I mean, this u intersection a is a finite set. So then we should get some contradiction. So if this is the case, if u intersects with a at finitely many points, then u intersects with this set a set minus x. So this set will be will also be a finite set because we are removing just one point from a, and now this set being a finite set and removing a point from a, then this intersection will also be a finite set. So then u also intersects. So then then u intersection with a set minus x is also a finite set. Assume that suppose that this, so suppose u intersection a set minus this x. So suppose it's a finite set containing the pointers x1 x2 through xm. So obviously it's a finite set. Now if this is a finite set and we know that this space x satisfies the t1 axiom, then this set has to be a closed set. So since x satisfies t1 axiom, then x1 through xm is a closed set, and hence the complement of this set is an open set, and hence u, which is equal to the complement of this set, is an open set. Now note that since this is the intersection of these two sets, so this set does not contain this x. That means its complement contains x. So we have an open set containing x. So then u is an open set containing x. And by hypothesis, what we have assumed at the first place, we have assumed that any open set which contains x contains infinitely many pointers of a. So then u is an open set containing x, and if we look at if we look at this intersection here, x1 so on, if we look at the intersection of these sets, this set with a, this has to be empty, because what x1 through xm is, so it is actually intersection of, let us call this set v, because we have already used the notation u here, so let's call this v. So since this set is this intersection is this set, that means if I look at its complement, so then x1 x2 through xm complement, if I look if I look at this complement and take its intersection with a set minus x, this has to be an empty set. So then this is an empty set, that is v intersection a is empty, because their intersection is a finite set x1 to xm, so its complement has no point common with a. But that contradicts our assumption, because what we assumed here, we assumed that every open set that contains x intersects with a in infinitely many points. So this is a contradiction to the assumption. We have assumed any open set u which contain x contains infinitely many points of a. This intersection is finite, but what we got here, we got an open set v which contain x, and its intersection with a is empty. So that is not going to happen, because that is our hypothesis. So hence this intersection over here, this is an infinite set. So hence u intersection a set minus x is an infinite set. Now let us define the sequences. So suppose we have a topological space, say xt. So this is our x here, and suppose we have a sequence of pointers, say xn, where n goes from 1 to infinity. So this is this sequence x1, x2, so on. So like this is x1 here, this is x2 here, so on. It is the sequence of pointers here. Now we say that this sequence xn, this converges onto a point, say x naught of x, if for every open set u containing this x naught, there is some stage, I mean there is some m in n, such that after that stage all the terms of the sequence is in u. So what I mean here, so if I take this open set here, so suppose this is x1, this is x2, this is x3, this is x4, this is x5. So if I take this open set u, then for this this open set u, this contains this point x naught here. Now for this open set there is a stage, I mean there exists a natural number. So in this case we have m is equal to 6, because the terms x1, x2, x3, x4 and x5, they are outside of the open set u. So for this open set u, m is 6. I mean if I look at the terms xn, where n is bigger or equal to 6, all the terms of the sequence are in u. Now if I take this u to be a small open set, so then this m increases. I mean so we have x6 here, x7 here, x8 here, x9 here. So for every open set there exists a stage in the sequence after which all the terms of the sequence are in that open set which contain x naught. So let us make a definition here. So let xt be a topological space, then a sequence xn where n goes from 1 to infinity, which is same as x1, x2, x3, so on. So this is a sequence of pointers in x. So this is set to converge to x if for every open set, to every open set u containing this x, I mean the limit of the sequence containing x. So for every open set u there must exist a natural number, say small m in n, such that all the terms of the sequence are in this open set whenever this n succeeds m. So if for every open set u containing x there exists some m in n, I mean there exists some natural number m in n, such that the terms of the sequence are in u for all n bigger or equal to m, then we say this xn converges to u. So if this sequence converges to x, then we write limit n goes to infinity xn is x, or we write xn converges to x when n goes to infinity. Now there are sequences, there are topological spaces where a sequence can converge to more than one point. For example, if I take the n-discrete topological space, so suppose we have a set x and let us take the n-discrete topology I on x, so that means in I we have only two open sets, the empty set and x. Now let us pick any sequence, say let us pick the sequence xn where n goes from 1 to infinity, then any point of x is a limit point of x. So why this is the case? So let us pick any point, say x in x. Now when do we say this sequence xn converges to x? So if there is some open set u containing x, now that u has to be non-empty because this x has to be an element of that set. So that means in over n-discrete topology that open set u is x itself. So that means for every open set u which contain x, so there must exist a natural number, say m in m, such that every term of the sequence is in u whenever this n succeeds m. So now in this case all the terms of the sequence are in the x, which is in our case the open set. So since there is only one open set in x and each term of the sequence is in x, so that means the stage for that open set is 1. Whenever n succeeds 1, each term of the sequence is in x. So hence this arbitrarily chosen point in x is the limit point of x. So same is the case with any point in x different from x. So in these kind of topological spaces, a sequence can converge to more than one point. But if this topological space is a Hausdorff space, then any sequence can converge to at most one point. So let us make this a theorem. So if xt is a Hausdorff topological space, then a sequence in x converges to at most one point. So let us prove this. So let xt be a Hausdorff topological space, and let xn, where n goes from 1 to infinity, be a sequence in x such that this xn converges to x in x. So what we have to prove? We have to prove this sequence converges to at most one point. Now it is given that this sequence converges to x. Now if we pick any element y in x and such that this y is different from x, then we have to show this sequence cannot converge to y. So that is what we have to prove. So let y belongs to x such that y is not equal to x. So we wish to prove this sequence cannot converge to y. So we want to show that xn can, we want to show that the sequence xn, where n goes from 1 to infinity, cannot converge to y. Now our space is given to be a Hausdorff space, and we have two distinct pointers, so we can separate these two distinct pointers by two open sets. So let u and v be open sets containing x and y respectively. So these are our open sets which contain u and v. These are the open sets which contain x and y respectively. So now, this being a Hausdorff space, then the intersection of v and u is empty. So then u intersection v is empty. So let us write one more point here. So let x belongs to u. So we have an open set u that contains x. Since this sequence converges to x, that means for this open set u there exists a natural number m in n such that each term of the sequence is in u for all n bigger or equal to m. So then there exists m in n such that xn is in u for all m bigger or equal for all n bigger or equal to m. That means this u contains infinitely many terms of the sequence, because this when n succeeds m, then each term of the sequence is in m. That means xm is in u, xm plus 1 is in u, and so on. So note that u contains infinitely many points of this xn. So since u intersection v is empty and only the finite this u contains infinitely many terms of the sequence, then there are only finitely many terms of the sequence which are not in u, and there is this case that those finite terms in those finite terms of the sequence are in v. So this v cannot contain the infinitely many terms of u, because their intersection is empty, and u contains all the terms of the sequence when n succeeds m, xm, xm plus 1, so on. These all terms are in u, and the only terms which are not in u are x1, x2 through xm minus 1. Now these terms, they may either belong to v or they may be outside of v. I mean there is this condition on V, that this V can contain at most finitely many terms of the sequence. So then V contains only finitely many, I mean this V contains only finitely, so V contains, I mean then V may contain only finitely many terms of the sequence. Now note here this Y is in V, so we have an open set V which contain Y. So now this open set contains only finitely many terms, so this Y cannot be a limit point of the sequence, because for Y to be a limit point of the sequence, then for this open set V there must exist a stage in the sequence such that for when we surpass that stage, each term of the sequence has to be in the V. So since Y is in V and V contains finitely many terms of the sequence, so Y cannot be a limit point of the sequence. X n, why this n goes from 1 to infinity. So if this sequence is converging to X and we have any point Y which is not equal to X, then that Y can never be a limit point of the sequence. In other words, this sequence can converge at most to one point. So this completes the proof.